So in Rutherford's atomic model, we have seen that the concept of nucleus was first time put forth by Rutherford, that the positive charge is completely residing inside the nucleus, which has very small dimensions, and the electrons are revolving around this nucleus in different circular orbits. But the Rutherford's model is not a stable model. So we have seen that on the basis of Maxwell's electromagnetic theory, the charged particle, when in accelerated motion, should emit electromagnetic radiation. So the energy of the electron will continuously go on decreasing, its radius will decrease, and finally it will collapse into the nucleus. So this is not a stable model. And one more difficulty is that because of this, the radius of the orbit of the electron is continuously decreasing. It is radiating the energy, so the spectra will appear continuous or a broad spectrum. Whereas practically it is observed that the spectra of hydrogen atom or the other elements, they are not the continuous spectra or broad spectra, rather they are line spectra. Certain spectral lines of specific wavelengths are observed in the spectra of the elements. So therefore Rutherford's model could not be accepted. So today we are going to study the next atomic model, which was put forth by Bohr. So this particular model actually based on certain concepts which are very new by the time. The Planck's theory came forward in the year 1901. So Bohr has used some concepts from Max Planck's quantum theory. So let us see first of all the different postulates which Bohr has proposed in his theory. So according to Bohr, in the first postulate he has mentioned that only certain circular orbits are stable. These are stationary, or more precisely one can say that these orbits are quasi-stationary. An electron does not emit electromagnetic radiation when in one of these states or orbits. So in Rutherford model, it was assumed that the electron can revolve in any possible circular orbit. But according to classical theory or the Maxwell's electromagnetic theory, this is not possible. So therefore Bohr has assumed certain stable orbits where the electron does not emit electromagnetic radiation. So these radiations he called as the stable radiations or the quasi-stable radiation. So this is the first postulate. Then the second postulate is that if you assume two different energy states or orbits, for example, the orbit I, initial orbit I, and the final orbit F. So if they represent two stationary states of an electron, and if the electron goes from the orbit I to F, where the energy of the electron in orbit I, that is EI, is greater as compared to the energy of the electron in the final orbit EF. So EI is greater than EF. So when there is this kind of transition, the electron will emit electromagnetic radiation. Because of this transition, there will be emission of electromagnetic radiation, and this particular radiation will have energy, that is E is equal to h nu, that is equal to EI minus EF. That means the energy difference between the two states. And the frequency of the electromagnetic radiation given out in this particular transition, that is nu is equal to EI minus EF upon h. So this is second postulate. And in the third postulate, Bohr has mentioned that the electron can only have an orbit for which the orbital angular momentum of an electron L takes on discrete values. That means the orbits are quantized. So L is equal to NH upon 2 pi. So in the first postulate, he has mentioned certain condition. All circular orbits are not allowed. Only certain orbits are allowed, which he called as the stable orbits. So the condition for the stable orbit is that the angular momentum should be integral multiple of h upon 2 pi. So L is equal to NH upon 2 pi. So this is what the quantization. And this concept is taken from Planck's quantum theory. So the angular momentum here is quantized. L is equal to NH upon 2 pi, where h is Planck's constant. H is Planck's constant. So here obviously the orbits of the electron are characterized by angular momentum, and it depends on both the distance of electron from nucleus and its velocity. So let us go through certain analysis or some mathematical derivations in order to understand this Bohr's atomic model, especially for hydrogen atom. So you know that when the electron revolve in certain allowed orbits about the nucleus, so it will be under the action of Coulomb's force, and this Coulomb's force is given by F is equal to JD upon 4 pi epsilon 0 into E upon R square, where E is the charge of electron, R is the distance of the electron from the nucleus, and JD is the positive charge residing inside the nucleus. So this is according to Coulomb's law of electrostatic force. Okay, so this is the force experienced by the electron. This force is balanced by the centripetal force. So the electron is performing a circular orbit, so there will be a centripetal force. So this force F is given by mv square upon r. So m is mass of the electron, v is the velocity, and r is the radius of the orbit of an electron. So from equation 1 and 2, if you equate these two forces, so they are balanced, therefore you can equate them. So m square upon r, that is equal to jd upon 4 pi epsilon 0 into E upon r square. So from this, if you rearrange the terms, so if you take this r to this side and if you multiply both sides by m, so left hand side will become m square v square and right hand side will be 1 upon 4 pi epsilon 0 m z e square upon r. So this is equation 3. Now according to Bohr's third postulate, we have seen that he has given certain condition for the angular momentum. So it is quantized. So L is equal to NH upon 2 pi. So that was the condition according to the third postulate. But L, that is angular momentum, you can also define in case of circular motion. You have studied that L can be defined in terms of the linear velocity. So L is equal to mvr. Okay, L is equal to mvr. So mvr is equal to nh upon 2 pi. So if you rearrange the term here in this equation, if you take this r to the right hand side, so mv will be equal to nh upon 2 pi r. And if you square both the sides of this equation, m square v square, that will be equal to n square h square upon 4 pi r square. Suppose this is equation 4. So earlier equation 3 we have derived. So there also we have the term here, that is m square v square. So if you equate this m square v square in equation 3 and equation 4 here, so let us see equating these two, what we get here is 1 upon 4 pi epsilon 0 into m z square upon r, that is equal to n square h square, this term n square h square upon 4 pi r square. So if you rearrange the term here to find out the equation for r, what you get here is r is equal to epsilon 0 n square h square upon pi me square z. So suppose this is equation number 5. Okay, so we have derived this equation for r. R is the radius of the orbit. Now for hydrogen atom, you know that Z, that is the atomic number, that is 1. We have only one electron and proton in a hydrogen atom, and the radius of nth orbit of the hydrogen atom. So n, why n? Because r is function of n here, you can see here. So you can use the suffix n to represent r. So Rn, that is given by this equation, Rn is equal to epsilon 0 n square h square upon pi me square. So Rn is directly proportional to n square, because rest of the terms epsilon 0, h, pi, m, e, all these are constants. So where n is called as the principal quantum number, n is called as the principal quantum number, and it take all possible values 1, 2, 3 and so on. So this is the principal quantum number, and if you substitute the value of n is equal to 1, and if you substitute the values of other constant, that is epsilon 0 permittivity of free space, then h Planck's constant, the value of pi, m mass of the electron, e charge on the electron. So what you get here is R1 is equal to 0.53 angstrom unit. So it is the radius of Bohr's first orbit. So like this you can find out the radius of the stable orbits, Bohr orbits, by substituting the values of n and rest of the constants in this particular equation for Rn. Okay, so after this we are going to discuss about the energy levels. So the electrons are revolving in certain specific circular orbits only. So depending on in which orbit the electron is there, so it will possess different energy. So because of this, the position of the electron, there are certain states, energy states associated with the electron. So this we can call as energy levels. So let us now try to find out these different possible energy levels in case of hydrogen atom. So according to third postulate, you know that the L, that is the angular momentum, in terms of linear term you can write it as mvr, that is equal to nh upon 2 pi. Now if you substitute this value of r in this equation, r, that means the Bohr radius. So if you substitute this value of r here, and if you rearrange the term to define the value of v, that is velocity, so we can have v here. If you take m and r to the right hand side, and if you substitute the value of r, what we have here is v is equal to nh upon 2 pi, as it is. This m here we have taken to the right hand side, and if you substitute this value of r, 1 upon r, so this will be inverted here. So what we have here is pi m e square upon epsilon 0 n square h square. So this is what the velocity, and if you just cancel out the common terms in the numerator and denominator, what you get finally is velocity v is equal to e square upon 2 epsilon 0 nh. So this is suppose equation number 6. Now from this velocity, equation of velocity, you can write the equation for the kinetic energy of the electron, because we are going to define the energy states of the electron from its position, that means in the different orbits. So kinetic energy of the electron, that is equal to 1/2 mv square, and if you substitute the velocity here in this equation, velocity square, so this square, so what you get here is, by substituting v in the equation for kinetic energy, so kinetic energy is equal to m e raised to 4 upon 8 epsilon 0 square n square s square. So this is the equation for kinetic energy. Okay, so now we shall define the potential energy of an electron. So depending on the position of an electron inside an atom, that means in a particular orbit having a radius r, so the work done in bringing the electron from infinity to that point r, or that distance r from the nucleus, that you can just find out by taking this integration. So the potential energy U is equal to integration over the limits r to infinity f dot dr. So why what does it represent, f dot dr? It represents the work done in bringing the electron from infinity to that orbit at a distance r. So this work done will be stored as a potential energy. Okay, so if now F is the Coulomb's force. So if you substitute this Coulomb's force here, 1 upon 4 pi epsilon 0 into z square upon r square dot dr. So and if you simplify this this particular integral, you will get the solution of this integral will be minus me raised to 4 upon 4 epsilon 0 square n square h square. So this is the potential energy. So total energy of the electron will be kinetic energy plus potential energy. So we have this kinetic energy, we have this potential energy. So total energy will be me raised to 4 upon 8 epsilon 0 square n square s square minus me raised to 4 upon 4 epsilon 0 square n square h square. Okay, so if you simplify this particular, so finally total energy E will be equal to, we are using suffix n here, so En, that is equal to minus me raised to 4 upon 8 epsilon 0 square n square h square. So why we have used n here? Because if you see in this particular equation, m, e, epsilon 0, h, all these are constant. Only thing, n is variable. So n is the principal quantum number. So therefore En is directly proportional to 1 upon n square. Excuse me. Okay, so En is directly proportional to 1 upon n square. So energy of the electron in the nth orbit. So if you substitute the values of all these constants, m, h, e and epsilon 0, so what you get here is n is directly proportional to minus 13.6 upon n square in terms of electron volt. Now if you substitute n is equal to 1, the energy will be minus 13.6 electron volt, E2 will be minus 3.4 electron volt. E2 means for n is equal to 2, so n square will be 4 here. So by substituting the values of n is equal to 1, 2, 3 and so on, you will have this respective energy. Okay, these are actually with a negative sign. I have just written only magnitude, but it is actually having negative sign here. So negative sign actually indicates that the force of attraction, there is a force of attraction between the electron and the nucleus. That means the positive charge residing in the nucleus. Okay, so these are the different energies you can estimate now for higher energy levels also. So when electron is in different orbits, it possesses this amount of energy. So from this you can draw a particular diagram that is called as a energy level diagram of hydrogen atom. So on this side you can say this is representing a quantum number. So from the lower side, quantum number n is equal to 1, 2, 3, 4, 5. So for these respective quantum numbers, we have this particular energy. So horizontal lines we have used to represent the level, energy level on the energy scale, you can say, in terms of electron volt. So minus sign, that means it is the lowest energy, minus 13.6. So n is equal to 1 represent the energy level where the energy of the electron is lowest, and that is called as the ground state of the electron in hydrogen atom. Okay, this is specifically we have discussed with respect to hydrogen atom, because Z we have already substituted, that is equal to 1. So you can say this is the energy level diagram of hydrogen. Okay, so as you go higher, you can say n is equal to 2. So n square, En is inversely proportional to n square. So initially you can see the difference between the two energy level, adjacent energy level, is much higher. But as the n value increases, this will go on decreasing. The energy difference between the two adjacent levels will go on decreasing, and finally when you reach to the higher value of n, they are very close to each other. They will be very close to each other. So this diagram represent the energy level diagram of hydrogen. So the electron can have any one of these particular energy level. So this is a specific representation of energy states of hydrogen atom. So for any element you can represent likewise the energy level diagram. So energy levels are very important, and this is the specific characteristic of that element. So for different elements there will be a different set of energy states associated with that particular element. Okay, so now we shall discuss about the origin of line spectra. Okay, so why we are getting line spectra for different element, and Bohr has explained from his second postulate. Okay, so according to we have already seen the second postulate. According to second postulate, transition of an electron from higher energy level, if you assume n2, to lower energy level n1, result into emission of photon of energy, that is En2 minus En1, that is equal to h nu. So the difference between the two energy levels, so that will be given out in the form of a photon of energy h nu. So earlier we have defined the equation for energy, that is equation 9. So if you substitute by assuming the values of n as n2 and n1, you can write En2 minus En1, that is equal to minus me raised to 4 upon 8 epsilon 0 square n2 square h square minus the other value, that is n1. So minus, again minus me raised to 4 8 epsilon 0 square n1 square h square. So this minus minus will become plus, and this en2 minus en1, we have seen that it is equal to h nu. So left hand side is h nu, and to the right hand side we can take this term common. What is that term? Me raised to 4 upon 8 epsilon 0 square h square. In bracket we have 1 upon n1 square minus 1 upon n2 square, because this minus minus will become plus. So 1 upon n1 square will be first because it is plus, and minus 1 upon n2 square. Now if you substitute here nu, that is frequency, you know that it is equal to c upon lambda, where c is the velocity of light and lambda is the wavelength of this particular radiation. Okay, so if you substitute that, and if you take this, so on the left hand side we have hc upon lambda, and if you take h and c to the right hand side, so what you have here is, to the right hand side, this will be multiplied by c, and h square will be multiplied by h, so that will become h cube. So this constant will become me raised to 4 upon 8 epsilon 0 square ch cube, and inside the bracket 1 upon n1 square minus 1 upon n2 square. Okay, so this is 1 upon lambda. Now in spectroscopy, this 1 upon lambda is very important term, because while representing the spectra, instead of showing a wavelength of the particular spectral lines, it's a very convenient to represent the terms by using 1 upon lambda, and this is called as a wave number. In spectroscopy, this is called as a wave number, and it is denoted by nu bar, wave number nu bar. So 1 upon lambda is a wave number and represented by nu bar, and it has dimension of meter inverse, okay, or in CGS centimeter inverse. So this particular equation, now just you can see here 1 upon lambda is equal to this common term, and in bracket we have this 1 upon n1 square minus 1 upon n2 square. So this particular term, all these terms involved in this are me epsilon 0 ch. If you substitute all these constant, this will become a constant, and this is called as a Rydberg's constant. This is called as a Rydberg's constant. So now 1 upon lambda, that is nu bar, that is a wave number nu bar, that is equal to r, that is a Rydberg constant, into inside a bracket 1 upon n1 square minus 1 upon n2 square, and the value of r, that is Rydberg constant, r is equal to 1.097 into 10 raised to 7 meter inverse. Okay, now according to the second postulates, whenever there are transitions, a photon of certain wavelength will be given out, or certain wave number will be given out. And if you consider this for hydrogen atom, and if you constitute and if you represent all these transitions, possible transitions, so you will get certain series, okay, certain series of photons of certain wavelengths, and that constitute a spectra of hydrogen atom. So let us see now this hydrogen spectrum. So in this particular diagram, the horizontal lines, you can see this horizontal line, they represent the levels, energy levels corresponding to the principal quantum number. For example, this is the ground state level, n is equal to 1. This is the second level, n is equal to 2, n is equal to 3, 4, and so on. Okay, now if you assume the first set of transition, you can see I have shown by this blue line all these transitions from the higher energy level to the first energy level, that is n is equal to 1. So that constitute a particular series of the wavelengths, and that is called as a Lyman series. So all these particular transitions will given out the photons which will lie in the ultraviolet region. Okay, in electromagnetic spectrum, you know that all these wavelengths to the very near to visible, to the left of visible, that is ultraviolet. So they are having smaller wavelength than the visible, that means they are having higher energy. So initially you can see that the energy difference is too much, so energy is higher, so therefore wavelength is smaller. So all these transitions, because of these transitions, photon given out, they will lie in ultraviolet region, they will lie in ultraviolet region. So from transition from n2 to n1, n3 to n1, n4 to n1, and so on. So all these transitions will give out photon, so that from a particular group or series that is called as the Lyman series, named after the scientist. So all these particular wavelengths associated with this transition, they will lie in ultraviolet region. So this is the first series. If you go to the next series, which I have shown by these yellow lines, now these are the transitions towards n is equal to 2 from all those higher energy level. That means the transition from n is equal to 3 to 2, 4 to 2, 5 to 2 and so on. Okay, so because of these transitions, photons will be given out of certain wavelength, and all these photons, they will lie in a visible region of the electromagnetic spectrum. Okay, so approximately 4000 to almost 8000 angstrom unit, and that constitutes a series that is called as a Balmer series. Now next, if you go further, all those transitions towards n is equal to 3 from the higher levels, that means from 4 to 3, 5 to 3, 6 to 3, 7 to 3 and so on, that will constitute another series that is called as Paschen series, and all those photons, they will lie in near IR region. IR means infrared. Okay, so if you go to the right of visible region in electromagnetic spectrum, the wavelengths are infrared. Okay, so very near to red, this is called as near IR. Okay, near IR, that means the near infrared region. And this is the third series. Further, if you go to next kind of series, that is a bracket series, the transitions involved here are from all those higher levels to n is equal to 4. That means 5 to 4, 6 to 4 and so on, and that will constitute a series that is called as bracket series, and all those photons having wavelengths in the range of infrared. So IR, you know that IR we can divide into three groups: near IR, IR and far IR. So this is a wide region here. Okay, so the wavelengths very near to red of visible, they are near IR, then slightly greater than that, they are IR, and far away from the red, they are called as far IR. Okay, so the next series is P-Fund series, and this results due to all those transitions to n is equal to 5 from the higher level, that means from 6 to 5, 7 to 5, 8 to 5 and so on. So this particular diagram represents the spectrum of hydrogen. This represents the spectrum of hydrogen element. Okay, so this is a very interesting thing. So the concept of transitions among the different energy levels, this was first time proposed by Bohr, and therefore this could explain the line nature of the spectra of the element. So why we get a line spectra, that could be explained from this particular concept, the concept of transition from one energy level to the other energy level. So these spectral lines are representing the hydrogen spectra. This is representing the hydrogen spectra. So the important achievement of Bohr's atomic theory or atomic model is that it could successfully explain the spectra of hydrogen atom, But there are some limitations also, limitations of Bohr's atomic model. So what are these limitations that we are going to discuss here? So first and very serious limitation of Bohr model is that it cannot explain spectra of atoms with 2 or more electrons. So only hydrogen spectra could be explained by the Bohr's model. If you go to the elements having higher atomic number 2, 3, 4 and so on, the spectra could not be explained by using Bohr's atomic model. Then another limitation is that it cannot give details of fine structure of spectral lines. So one of the line in hydrogen spectra, that is the H alpha line, it actually not a single line. When it is observed through a high resolving power spectrometer, it was observed that it is actually a group of two spectral lines which are closely spaced. The spectral space between these two is only 1.4 angstrom unit. So these are two lines, not a single line. And what is the reason that could not be explained by the Bohr's atomic model? And one more important thing, Zeeman effect. You know, Zeeman effect is what? When you apply strong magnetic field, then it was observed that the spectral lines of the spectra of certain the elements, it was observed to be splitted. So one single line split into three or more, depending on whether it is a normal Zeeman effect or anomalous Zeeman effect. So this Zeeman effect, that is splitting of the spectral lines due to application of strong magnetic field, that could not be also explained by Bohr's atomic model. So these are some limitations of the Bohr atomic model.